So, hi everyone, how are you doing today? Myself Ketan Thora, the community manager of ML Nasik, and yesterday we had Pratik with us, who actually had the evaluation metrics with who taught us evaluation metrics, and now today we have Pranav Ahire with us, who is going to teach you about neural networks. So, hi Pranav, how are you doing today?
Hello, Ketan. Yeah, I'm fine.
Hi.
How about you?
I'm also doing great. So, yes, today you're going to teach about neural networks. So, I'm just handing over it to you.
All right. Yeah, so
Yeah, good.
I'm actually pretty excited to take this session. And
Yeah,
yeah,
cool.
so we'll be looking at this session
Something
shortly.
about yourself, like let audience know about you, what you do,
Okay,
and all.
yeah. So hello everyone. My name is Pranav Ahire. I am also a fellow ML enthusiast like you guys. I am a third year undergrad and I'm pursuing data science as my major.
Okay,
And yeah, that is pretty much about me.
yeah,
And we
that's
will
cool.
look at we'll start in like 1 or 2 minutes. Okay.
Sure, I'm handing over it to you. Then
All
till
right, yeah.
then, I will go upstairs. Yeah, good.
All right, so I'll just present my screen now. Share. Present. All right. Yeah, so I can see some people. All right, so if you can, by the way, you can, if you can just listen me and see me, just put down a thumbs up or anything so that I can get a message that we are live. And yeah, we'll start in 1 minute. Okay, yeah. All right, so welcome everyone. Good evening. Welcome to the ML Math Club by ML Nasik, and today we'll be looking at neural networks. So, yeah, how many of you are new to deep learning or let's say neural networks, or how many of you are aware of what exactly is neural network, or you have just heard something about it? Okay, no worries. If you are new to this, we can just start out, and take you. Uh, I'll just show you what are the things we'll be looking at today, right? So today's agenda is simply simple. We are going to quickly go through linear regression and gradient descent, which was the topic of our first session. Later on, we'll see what are the drawbacks of native machine learning, and we'll also see where exactly deep learning shines, right? What are the drawbacks of native machine learning, and why there was a need of deep learning, or why deep learning is so popular in today's world, in today's century, right? After that, we'll study basics of neural networks, that is called as a perceptron, a basic artificial neuron that is called as a perceptron. After perceptron, we'll study some basic techniques, which are forward propagation and back propagation, which are basically a technique by which the data or flows in a neural network. Okay, so let's start. And yeah, so here's my board, and sure. So I hope English is fine, right? You guys are comfortable with English, right? So let's start with the very first topic, is that is linear regression. Okay, right. इसको थोड़ा छोटा कर लेते हैं, and let's erase this and let's start. Okay, so we'll be looking at a very simple topic which is just linear regression. Okay, and this maybe we'll just look at simple linear regression, not a very complex right now. We'll just look at simple linear regression. Okay, so let's just imagine a simple example, and in this example, I'll consider myself, right? Let's imagine I am a data scientist at some particular construction company, right? Let's For now we live in Nasik, right? So let's consider example of Runta builders. Okay, so what they do is they are construction workers, basically, who build buildings, basic flats and stuff, right? So I am a data scientist at Roomta Builders, and one it's a normal day, and one day my manager comes up to me and he's like, "Pranav, I have this past data, okay, and past data of basically he has past data of house prices, okay." And he comes up to me and he says, "Pranav, I have this data. I want you to train a machine learning model, okay. I want you to train this machine learning model on this particular past data, so that in the future, whenever I'll give some input to this particular model, it will be able to predict the house price, okay." So our task is simple. We have the data. What we have to do is we simply have to train a machine learning model, and then we have to make a prediction. Okay, simple task. Okay, so I got the data. So the very first thing which I did was I just took a simple snapshot of the data, like what exactly the data contains, right? How many column does it have? What exactly is the prediction? What exactly is the target column, right? And what I have to do. But initially, I said that we are going to look at simple linear regression, right? So in this particular problem, or let's say in this particular branch of linear regression, we are going to have a single feature column, okay, single feature or a single input column, and we'll be having a single output column. Of course, we in regression problems we don't really have multiple outputs generally, okay. And inputs are also called as features. Okay, so I have one input column and I have one output column. Okay, and what I have to do is I have to simply predict what can be the house of unseen data. Okay, so let's imagine I have let's say I have 10,000 instances in my data as of now. Let's just take a very vague example of 10,000. Okay, so what I did was I saw the very first instance. Okay, let's imagine this particular thing is nothing but area. Okay, like what exactly is the area of your house or your flat, right? So let's say, for instance, let's say 800 square feet. Okay, so we have the price of 800 square feet house in Nasik is roughly, let's consider it's roughly 30 lakhs. All right, a very random example again. I don't know what exactly is the current scenario right now, but anyways, moving forward, let's take another example. Let's say I have another flat which has an area of 1,000 square feet. Okay, and this flat costs around 45 lakhs. Okay, so what I did was I I did not manually looked at all the data points. What I did was I simply took all the x values, basically all the values of my area of individual flats, and what I did is made I simply plotted the distribution of my inputs, my area of individual flats with respect to the price of each flat. Okay, and I got something like this. I got a distribution which looks something like this. Okay, a simple intuition. I'll just show you intuition what exactly I mean in a moment. Okay, so let's say this is 800. Okay, this is 800 square feet. So at this particular point I got a price of, let's say, 35 lakhs. Okay, so this particular point, the 800 shows this particular point, and this is like my x and y. Okay, so this is 35 lakhs. So what I basically did was I took all the instances, I plotted them on x-axis with respect to their individual house value, like price value. Okay, and now I got to see that this particular data is a linear distribution of data. Okay, so what do I mean by linear distribution? Simply, if my x increases, my y is also increasing, right? Similarly, and vice versa. If my x decreases, y also decreases, right? So this is nothing but linear data, right? It shows a linear property, right? So at this point, I'm able to understand. Okay, generally you're not able to see this distribution. This is a very simple problem with only one input feature, so that is the only point we are able to plot this particular distribution. Generally, we have uh, hundred or thousands of features. So it is a multidimensional distribution, and we are as humans we have not exceeded our visualization capabilities beyond 3 dimensions. So it is very difficult for us to even imagine how multidimensional data or multidimensional distribution looks like, right? But at this particular point, we are just using a very simple one-dimensional distribution, right? So at this point, I understood कि ठीक है चलो, I have a single input, I have my output, but how can I model this particular data so that whenever after training my model, I'll get the very best estimate of my input, whatever input I'm giving it. Okay. And for instance, I'll just draw out a line here, and then later I'll explain why I'm drawing this line. Okay. All right. So this is a simple line, and its equation is y mx plus b. All right. Simple line equation. Okay. So why we are plotting this line, right? Because what at the end of training, what are our expectations, right? So we want a model which covers almost all the points, but not only it covers the points, it is as close to each and individual point, right? And if you just think about it, you'll get to know that if somehow I'm able to find the center of this particular distribution, or somehow if I'm able to plot or draw a line from the center of this distribution, that particular center is the closest to all the other points, right? So that is simply we are doing over here. Okay. And let's just understand it even better. All right. So this is my line. Okay. And this line is the closest to all the other points, right? So, but let's just imagine this is the best line, right? At this point, this is the best line. But for now, let's just imagine that this is not the best line, and we are still yet to figure out. We have to still figure that which exactly is our best line. Okay. So what I can do is I can find my error term, which basically means that I'm using my label values and I'm subtracting my model's prediction from it. Okay. So a simple example could be, if this is my particular label, let's say this is some yi value, and this is my model prediction at this particular xi. Okay. So what I'm doing is I'm trying to find this particular distance between my model's prediction and my original label, right? And I'm doing this with each and individual point in the data set. ठीक है? इससे क्या फायदा होगा? Simply I'll get to know कि मेरा like on an average मेरा लाइन कितना बेस्ट है, राइट? एंड इसमें जस्ट एक और चीज़ मैं बता दूं कि फॉर एग्जांपल जस्ट इमेजिन कि मेरा मॉडल का प्रेडिक्शन मेरे वाई आई से ज़्यादा हो गया, राइट? फॉर एग्जांपल इफ दिस इज सम पॉइंट, दिस इज सम माय वाई आई for this particular xi, and this is my yi hat, this is my model's prediction, and this is my original label, right? So clearly we can see over here that my model's prediction is greater than, right, its value is greater than my original label, right? So overall this value will turn out to be a negative value, right? We don't want that, because at this point we are only interested in absolute value, right? Distance cannot be negative, right? It will always be positive, right? So for that reason we'll square it. Okay, so it will automatically, even if it turns out to be negative, it will be positive at the end of the calculation. Okay, so what we did was we simply took the residual. This is called as a residual. We simply used the original labels, we subtracted our model's prediction, and we just squared it. Okay, so this is our error term. Okay, moving forward, next हमने क्या किया? We used our error term. This is nothing but yi minus yi hat square. Okay, then I realized ki, to be able to model this particular data distribution, this error should be minimum, right? And the best thing could be that this error becomes zero, but I'll later tell you why this is not possible. As of now, we'll just assume that we have to reduce this error as much as possible. Okay? And initially we knew that this is nothing but the Line's equation, and this is nothing but y is equal to mx plus b, for instance, yi xi. All right. So I'll just quickly substitute this particular equation in my error term. So this is nothing but mxi plus b whole square. Okay, right? So at this particular point, you can see that my error term depends only on two things. Okay, if you can carefully observe, right? I know my yi, what exactly my y is. It is my original label. It is my original label. My xi is my input. I know these two values. I just want to know. I just need to know these two values, and that too I have to figure out the minimum value of my m and b, so that my error term turns out to be the minimum value, and I'm able to model my data. Okay, so from here, using some basic calculus, we can figure out that we can actually make a relation between error and the residual, which is nothing but, we can say that my error is a function of m and b. Because why? Because m and b are the independent variables, whereas other variables are known to us, so they turn out to be dependent. And this will turn out to be yi minus mxi plus b whole square, right? So this is my original function, which I have to minimize. Okay, so initially we'll quickly look at closed form solution. The very first thing is we'll look at closed form solution. Okay, so closed form solution matlab it's very simple. It's basically हम क्या कर रहे हैं कि we are not using pretty difficult calculus at this point. We are just using some basic mathematics and simple calculus to derive the minimum values. Okay, so what I'll do is I'll just say that at this point, I have to find the minimum value of my error. So what I'll do is I'll simply differentiate this with respect to some particular m or b. Okay, like for example, I'll just take up an example. Let's assume at this particular moment, let's assume that m is constant and m is constant, and we have to differentiate with respect to b, right? For example, I'll just do that be by db is equal to 0, right? So I'm saying that at this particular differentiation, right, अगर मेरा slope 0 हो गया, so मेरा loss minimum हो जाएगा, right? मेरा error minimum हो जाएगा, and we'll quickly look at this at the moment. Ki what do I mean by slope 0 and all this? Okay, so I'll just quickly formulate this without wasting any time. So let's say 0 is equal to, we had this yi minus mxi plus minus b whole square. Okay, so I'm differentiating with respect to b, so this will turn out to be 2 into yi minus mxi minus b, and as we know that dy by dx of x square is nothing but 2x. So I've done this 2 minus 1 into minus 1. Okay, so this will turn out to be minus 2 into yi minus mxi minus p. This turns out to be 0. I'll just simply divide it by minus 2, so minus 2 cancel over here. I have the 0 yi minus mxi minus b. Okay, I'll just quickly shift my b over there, or let's say at this particular point, like for example, I'll just show you that solution again. Where it go? Right. So हम लोग यहाँ पे क्या कर रहे थे? We were calculating the minimum error, right? But we are doing this for all the models prediction, all the given original labels, right? So we'll simply do a summation over here, right? I is equal to 1 to n, a simple summation. Okay, why? Because हमें average चाहिए. I'll just quickly show you in a moment कि what do I mean by average and all this stuff. Okay, so initially we have, alright, so we have average over here, y minus mxi minus p. I'll just quickly open up the bracket. So this turns out to be y 1 to n yi minus m is a constant, so integration of y is equal to 1 to n xi minus summation of 1 to n b. Okay, and I'll just divide all these values by n. Okay, so this turns out to be right. This is a simple mean formula. If you know mean formula, you'll get to know that this turns out to be y average minus m x average minus b, because summation of b is nothing but nb by b, nn cancels. This turns out to be b 0, and I'll just quickly shift my b to the left hand side. So at this point, I have one of my value. This that is nothing but this. Okay, so this is my minimum value of b. If I just compute this particular equation, I'll get my minimum value of b. Okay, so initially हमने क्या देखा था कि my error is nothing but it is summation of I to n yi minus y mxi minus b whole square, right? So at this point, I have the value of b. I'll just quickly substitute it. I'm just not writing summation at this point, but it exists. Okay, later on I'll just quickly grab it, but at this point I'm not interested in writing summations. All right, so I'll just quickly shift my b up here. This turns out to be mx whole square. All right, so in this particular equation we don't really have b at this point, and I'll just quickly differentiate this particular thing with respect to m so that my error turns out to be 0. We'll later on look at the moment what do I mean by error term differentiating slope. Okay, at this point, just bear with me. We'll quickly look what do I mean in just a moment. Right, so I'll differentiate this. This turns out to be 2 into yi minus mxi minus y bar plus mx bar into, differentiating with respect to m turns out to be minus yxi plus x bar. All right. Yeah. All right, so I'll just take the minus common from here, minus 2 yi minus mxi minus y bar plus mx bar into xi minus x bar, right? I guess, yep. Okay, I'll just divide it by minus 2 cancels, and I'll just group the common terms together on one side and the rest on the other side, and yeah, this turns out to be this equation. Okay, and yeah, just a moment ago we saw that the summation still exists over here, so I'll just write summation here and x bar. Okay, at this point I'll just open up the bracket, so summation okay, so summation yi minus y bar into xi minus x bar minus m common xi minus x bar whole square, because after taking x common I'll have xi minus x bar, and after multiplying it with itself we get a square, and this is equal to 0. Okay, so I'll just quickly open up the summation alongside the bracket. So this turns out to be yi minus y bar into xi minus x bar minus ms constant xi minus x bar whole square, and this is 0. I'll just quickly bring this particular part to the LHS. So this is m summation of xi minus x bar square is equal to summation of yi minus y bar into xi minus x bar. Okay, yeah. Now we can see that we have m into this particular whole computation. So I'll just move this to the right hand side, and we have the formula over here, and yeah, we are almost done. Okay, xi minus x bar whole square, right? So this is our m value for which our error is minimum. Okay, so initially we had b, which was, if I'm not wrong, it was equal to y into x bar something, I forgot actually. Yeah, y bar minus mx bar. Okay, so this was nothing but y bar sorry, y minus mx bar, right? Yeah. Okay, so these are the two values b and m for which my error is minimum. Okay, so this is simply called as closed form solution, where we used simple plus minus and a basic difference calculus to calculate the values for which the error term is minimum. Okay, but moving forward, you'll realize that all these particular formulas will lead to high computations, right? Because just think about it for a moment. These are the values which will directly set your error to the minimum value, right? And here you can see there is a lot of computation, right? For example, just imagine if I have 10 million rows in my data, right? So at this point I'm doing summation of all those 10 million target values and all those inputs, squaring them in the denominator, then doing the summation on numerator and denominator, then dividing them. So it's a lot of computation, right? And we usually don't really have that much RAM in our system, so, which can accommodate this huge amount of data, right? So generally we don't really use closed form solutions in while implementing machine learning models, and we use a technique which is called as gradient descent. I know this is also something which was covered in the first lecture, but I just want to quickly go through it so that we are able to better understand how exactly neural networks work. Okay, so I'll just quickly look at, I hope this till this point you are I am clear and you're able to understand what we have seen till now. I just hope just give me a simple thumbs up and we'll move forward if I'm clear and if I am making sense right now. Okay, we'll move forward. No worries. Okay, so we'll quickly look at something which is called as gradient descent. Okay, right. So till this point, we were calculating two values, m and b, for which we get the minimum error. Okay, and this was our formula, right? Just think about a moment. You can see that later on we said that this is nothing but a function of m and b, and which looked something like this. Okay, think about it. What if I say that we have a function f of x which is nothing but x square, right? So if I just draw this function's distribution, it will look something like this, right? Which will completely resonate our error function's distribution, right? Our error function will have the same distribution as this particular f of x equal to x square, because after all these are functions and they follow the same property, right? At the end, this will turn out to be some constant at each particular point, and when we'll plot all these points, all these errors, or with respect to the loss, all these parameters, like for example all these parameters m or b, with respect to the loss, will get a distribution which will look something like this. Okay, at this moment just imagine that one of the parameters is known to us, let's say b is known to us, and we are just plotting this with respect to m. Okay, if we are plotting this with respect to both the parameters, then it will be a three-dimensional distribution, okay, which will look something like this. This is my x, this is my y, and this is my z. This will be my m, b, and this is nothing but my error. Okay, and in three dimensions it will just look like something like this. You can see this is your coefficient c1, which we can consider as b. This is my m, and this is nothing but my distribution of my error. We can also consider this as a loss, but we'll later look at. I will later call it loss. For now, we'll just call it error function. Error. Okay. Yeah, something like this. Okay. All right. So till this point, we saw the closed form solution, and we were able to derive two formulas, closed form solutions, two formulas for minimum value of m and b. Correct. But we later saw that this is computationally expensive. This is computationally expensive, and we don't really use this. Okay. Instead, what we do is we used a technique which is called as gradient descent. Okay, so what gradient descent simply means is I want the minimum value of my error. Okay, if you are familiar with graphs and all, you know that this is a convex function. A convex function basically means that they only have one minima, one global minima. Okay, so here we know that this particular convex function, or let's say our error function, has a single global minima, and we want this value of error with respect to this m. Let's just say we don't know, we know b, what exactly is the value of b, and we are not aware of what is my m value for which my error is minimum. Okay, so at this particular point, what gradient descent says is, gradient descent says ki, let's just imagine our error is over here at some particular m. Okay, so gradient descent says that, we'll calculate gradient or slope at this particular point, and what we'll do is we'll slowly move this gradient, move this gradient to this minimum value. Okay, so basically, if you are not aware with the concept of slope, so if you have if you are if your slope is decreasing from left to right like this, then you have a negative slope. But if your slope is increasing from left to right, then you have a positive slope. Okay, so at this particular point, our slope is decreasing, right? If we move from left to right, we'll have a slope something like this. For example, at this particular point, will have a slope something like this, right? So when I'm moving in the x direction from left to right, I have a slope which is decreasing from left to right, right? So my slope will be negative. Okay, but what I have to do is somehow I have to make this slope 0. Okay, so the horizontal line is 0, right? So if somehow I'm able to reach this particular point, this particular global minima, at this particular point my error will be 0 for this particular m value, right? So this is my optimum value. Okay, and for this we simply do a gradient descent step, right? So we do, right, for what we'll do is m new, right? So this m is nothing but m old minus my gradient with respect to error term with respect to my old gradient, right? But in machine learning, we don't really do very high transitions or very high computations, very high changes. So what we do is we simply add a learning rate here, which basically controls the movement of our gradient from this point to this point. Okay, so this is something, if you have attended the first two lectures, you must be aware what I'm trying to say. And yeah, that is pretty much it about it. That is pretty much about linear regression and gradient descent. So yeah, so we try to calculate the optimum values for weights for which our error, or let's say our loss, is minimum. Okay, so till this point, if I am clear and I'm making sense, so you can just drop a thumbs up or any reaction, and I'll get to know ki, okay, I am making sense. All right, no worries. I think we are good to go. We'll move forward. All right. So till this point, we saw gradient descent, we saw linear regression, gradient descent. Let's start today's topic, that is nothing but neural networks. Okay, but first let us just look at what were the drawbacks of native machine learning and why there was even a need of deep learning, right? Or why there was the need of neural networks, right? So what happens is, in native machine learning is, if you have a native machine learning model, let's imagine you have a native machine learning model, okay, and you have huge amount of data. Okay, so eventually you're training a model on huge data, but what you'll observe is, after a point, your model's performance will become stagnant, or it will just become constant after a point, right? Like, for example, if I am just saying this as right, let's just say this is data and this is performance. So after a while, you'll observe that you are increasing your data. Okay, your performance is increasing. You're you're giving it more data, it is performing better. But after a point, it will just become constant. It will just become stagnant. Okay. Whereas if you give your deep learning model huge amount of data, so eventually it just performs exponentially better, right? So one reason why deep learning shines is because deep learning works on unstructured data, unstructured, huge amounts of data, huge amount of data, and it just performs exponentially well. All right. So this was one part of why, this was one major drawback of why we started opting for deep learning. And as we all know that deep learning is nothing but a sub branch of machine learning, sub branch of machine learning. Okay. Next is high computation, right? So all our native machine learning models are CPU based. Okay, so if we are using some huge data set to train your model, there is a lot of tremendous high computation involved, and it will take a lot of time for your machine learning model to train, and it just becomes, after a point, it just becomes very difficult for you to eventually monitor your model. And it is simply, if you have more data, it just simply means more time in machine learning. This is the same case in deep learning, but there the performance eventually increases. So the trade-off is pretty good for us. It doesn't matter. Okay. The next thing is why deep learning shines is, let's just look at why deep learning shines. Okay. Next topic is why deep learning shines, right? And the major reason why deep learning shines is the GPU computations. Okay. So in deep learning computations, in deep learning, we use GPUs to train our machine learning model, right? So because of GPUs, we introduce something which is called as parallel computation, because of which we are able to train this on huge amount of data and somewhat reduce the training time. Not much. Deep learning models take tremendous and huge amount of training time, but somewhat reduce training time because of parallel computing. Okay. So at this point, we are clear with what is linear regression, we are clear with what is gradient descent, and we just saw what are the drawbacks of native machine learning, right? Let's just start with the main topic of today, that is neural networks. Okay. And let's start with the very first topic, that is nothing but perceptron. Okay. So a perceptron, I'll just quickly walk you through what exactly is perceptron. Okay. So a perceptron is nothing but it is a basic unit of neural network. Okay. And a perceptron is nothing but it is a artificial mimic of biological neuron. Okay, so basically I'll just quickly show you what do I mean by this, right? So let's just say I am saying biological neurons network, right? And we are just simply looking at a network. All right, so this is nothing but I think this is visible, right? So this is nothing but a biological neuron, and you can see that in this we have something which is called as axon, terminal buttons, and cell body, right? So we'll quickly look at what do we mention this in deep learning, right? Okay. All right. I hope I am audible. Is there a lag? Guys, can you just let me know if there is any lag? I think there is some lag. I am not really sure. Uh, no, I think we are good. Right? Okay. Am I audible to you guys? I don't. I just think I don't see any movement. All right. I think we are good. No problem. Anyways, let's move forward. So we'll quickly look at what exactly is a perceptron. Okay. So in neural networks, what happens is, right, in machine learning, what we were doing is we were basically calculating our output. Okay, and output was nothing but it was a simple summation of uh, our weights, but there's nothing but wi into our inputs plus some bias. Okay, so in neural networks, what we do is we use a concept of perceptron. So this basically is your perceptron, and what you do is you give it some inputs, let's say x1, x2, x3, and you get the output from this particular perceptron. Okay, I'll just quickly walk you through what other things are involved in this, right? So this particular operation, right, this is nothing but a weighted sum of inputs, right? So we so in a perceptron, all this is nothing but an edge. This is nothing but our artificial neuron, neuron, right? This is every edge has its own weight, right? For example, if this is a neuron, this is W1, for this W2, W3, and every artificial neuron will have its own bias. Okay, so how computation just works over here, I'll just quickly walk you through, right? So for example, what I'll do over here is I'll take my very first input, that is x1, I'll multiply it with my weight, that is w1, plus the next input w2 into its next weight, and the third input, last input, right? And I'll just quickly add the bias over here, and here we'll get our prediction y hat, that is nothing but our output. Okay, and this is the same thing which we were doing in machine learning. We were just calculating the summation of our weights input into our inputs plus our bias. Okay, so this is the same thing which happens inside a artificial neuron, or this is also called as a perceptron. Okay, this is nothing but a basic unit of a neural network. I'll show you what exactly is a neural network in a moment. Okay, so I think I am clear till now. Let's move forward. The next topic is nothing but multi-layer perceptron. Okay, and this is also a neural network. Okay, so till this point we saw that we have a perceptron. Okay, this is a perceptron. It has some inputs x1, x2, x3. It gives us some output after doing a weighted sum of weights into inputs plus bias term. Okay, but the thing is, in a perceptron, what we do is we give it a function, and this function is called as activation function. Okay, so why is activation function needed? It's pretty simple. Activation functions just simply adds non-linearity to your neural network, or to your perceptron. Okay, so why? So that we are basically, so what I mean is, it simply adds non-linearity so that you are able to classify, or let's just use a very general term, you are able to model your data's distribution. Okay, so this activation function is basically used to model the data distribution. Okay, so we saw that in a perceptron, we have weights, we have some inputs, we have a center which is called as a neuron. Here, basically, there are at this particular point two operations are operating at the same time. One is the weighted sum, and the other one is nothing but calculating the activation or sending this particular weighted sum into the activation function to get our output. Okay. Okay. All right. So let's look at what is multi-layer perceptron. Okay. So we saw that this is nothing but a perceptron. Okay. Let's just imagine I have another perceptron over here, and then one more over here, and I am connecting some more. I'm just having two more perceptrons over here and one more over here. Okay. So this particular thing, let's just call this a O1, O2, O3. Okay. So this is my first perceptron. This is my second perceptron. This is my third perceptron. What I'm doing is, at this particular point, whatever the output of my first perceptron is, I'm sending this particular output as an input to my next perceptron. Okay. I'm doing the same thing with all the rest perceptrons. Okay. All the rest two perceptrons. And the same thing is I'm doing for the next perceptron, which I've added below. Okay. Let's just call these perceptrons for the moment as O4, O5. Okay. And we are doing the same for the last perceptron. Okay. And let's just call this O6. I'm really sorry for my drawing. I'm pretty bad at it, but for now, just bear with me. In a moment, we'll draw it pretty nicely. Okay. So what I've done is I have some of my inputs. I've sent all those inputs to my individual perceptron. I have gathered their output and I've forwarded those outputs to the next perceptrons. Okay. And similar I've done for the last perceptron. Okay. Let's just draw it pretty nicely. I think that is pretty bad drawing. All right. So let's just see. We'll simply draw a simple multi-layer perceptron layer right now. Let's just say I have an input x1, another input x2. I have a perceptron artificial neuron over here, and over here. Okay. And this is nothing but my output. Okay. This is my input. This is my output. I'm connecting this to this. I am also giving this particular input to the next perceptron. I'm doing the same with the next input, and the output of both of these perceptron, I am forwarding it as an input for my third perceptron. Okay. So in neural networks or multi-layer perceptron, basically both are the same thing. We have three stages, or we can say we have three layers of building this particular large neural network. Okay. The very first one is what we call it as an input layer. This is nothing but a hidden layer. And the last one is our output layer. Okay, output layer. Okay, I'll just quickly walk you through the notations, right? So this is nothing but the input for the very first layers, first neurons, first input. This is the same. This is the input for first layers. This is my layer 1, this is my layer 2, and this is my output layer. This is my input for very first neuron. This is first neuron, and this is the second input for the first neuron, and similar goes to over here. Okay, right. All right. And this is the activation of my very first neuron. So first layers, first activation. Or let's just call this O11. Let's just call this O12. And here I have my weights, as we discussed earlier. Here we have our weights. So this is my weight of first layer, first neuron, first weight. This one is first layers, second weight for my first neuron. This is first layers. This is the second neuron, right? So right, so this is nothing but first layers, first input by second neuron, and first layer, second input, second neuron. Right? This is 2. and this is 1 2, right? Yeah, sorry, I got a bit confused. The same goes for here. This is my weight for the second layer's first input for first neuron, and the same over here, right? Second 1 2, right? And this is my output. This is O3. Let's just call it O3, right? It doesn't matter, right? A lot of mess. I'll just clear it in a bit. I'll just draw it a little better. First layer on 1 2 and W1 to 1. Alright, yeah. So yeah, it's pretty much correct. Right, so this is nothing but basic multi-layer perceptron. Okay, and when you'll add more neurons to this particular hidden layers, you'll have a very complex network, right? You can understand. Either you can do three things over here, right? Either we can add more inputs, okay, or we can add more neurons to these individual layers, or we can add more layers, more hidden layers to these particular networks, okay. And yeah, one more thing exists. Just imagine for a moment you have multi-class classification or multi-level classification. In that particular case, you will have multiple outputs. Multiple outputs. Okay, so I just hope I am making some sense, and you're at least trying to get an intuition that what we are trying to do over here. Okay, so let's just quickly get a MLP, or let's say a neural network intuition, that what exactly is happening over here. All right, so let's just say I have a very complex data distribution. Let's just say I have to do a classification problem, and I have my data distribution somewhat like this. Let's just say uh, these are my target variables, or this ones are the favored ones, and I have the other ones which I'll show it with the red cross. These are not the ones or my unfavored ones. Okay, so I'm trying to draw out a line over here, which basically tries to classify this particular distribution into two parts. One is my prediction or my favorable part, and the other is my unfavorable part. Okay, so at this particular point, this is a pretty simple distribution, right? So you just have to draw a line, and you can do this with a single perceptron also, right? A single artificial neuron also. Okay, but let's just take another example, and let's just make a pretty complex distribution, right? So at this point, let's just imagine you have a very complex distribution, something like this. Okay, these are your favored ones. Okay, and this is nothing but your unfavored. Okay, right? So here you just don't have to draw a straight line, rather you have to draw a line which looks something like this. Okay, just imagine it is a pretty complex distribution with some of the points over here. It basically is not a straight line. I've drawn it like I've drawn it in a way that we are simply able to distinguish it with the help of a straight line. But just for instance, just imagine it is very complex distribution, and we are not able to differentiate it with the help of a straight line, right? So in this particular case, we can use a simple neural network, which what it'll try to do is, see, we have some of our inputs, let's say x1, x2, x3, and we have our neurons over here, right? And let's just say this is output, right? So what individual neuron will do is it will try to learn some basic features, right? So for example, what this particular neuron will do is it will try to draw a line on this particular distribution in somewhat this manner, right? For example, this neuron, the first neuron, draws a line something like this. Okay, similarly, the second neuron which we have over here will draw try to draw a line which will look something like this. Okay. Similarly, the third neuron will also draw a line which somewhat look like, I don't know, like let's just say it looks something like this. Okay. So we have two more neurons, and this is our output neuron. Okay. So what will happen is each neuron will try to model the data distribution in some other way so that it is able to do some feature extraction at this particular first layer, at this hidden layer 1. Okay. Similarly, this is my initial layer, right? So this is my first layer. So at this particular point we'll have feature extraction, a basic feature extraction of our distribution, right? But moving forward, what deep neural layers will do is they will do some higher feature extraction. Okay, for example, what do I mean by a higher feature extraction is, imagine these three neurons did something like this. The very first neuron made a line like this, the second one did something like this, and the third one made a line which looks something like this. Okay, so this is nothing but a basic feature extraction which these individual neurons were able to do, right? But what the next neuron will do is it will combine its output, right? Sometime before we discussed that the output of a particular neuron is input for the next layer's neuron, right? So what the next layer neuron will try to do is it will combine the basic features and try to merge it into to identify some higher features, right? For example, it will try to draw some, it will try to model your distribution in somewhat this way, or let's say it will try to model it in somewhat this way. Similarly, the next neuron will try to model it. Similarly, for the next neuron, it will try to model it in some other way, right? For example, let's just say in some this way or anything like this. And eventually what will happen is when you will merge these two neurons output into your output neuron, what it will do is it will try to model it in a way that is that is perfectly trying to classify your problem. Okay, right? Initially I'll just go to our distribution. Okay, and I'll just remove these lines. I know my drawing is pretty hilarious, but just bear with me for a moment, right? So what will happen at this particular stage, at this last stage, is something is it will try to model it in some other way, like something like this, right? So this is nothing but your best fit line. Oh my god, this is nothing but your best fit line. Okay, which is modeling your data in the best way possible, right? So this is something which neural networks try to do. Okay, so it doesn't matter if your data distribution is very complex, given if your data distribution is very complex, right? So just our upward direction suggests that it is very complex. It doesn't matter if you have given enough neurons, enough hidden layers, and proper activation functions, then you'll be able to model any data distribution. However, it doesn't matter however complex that data distribution is. Okay, so this was a simple intuition on how deep neural networks are trying to work behind the scenes and how they model your data, right? So I think I was able to make some sense. I just hope I'm making some sense and you're at least getting some intuition on what is happening around this. Okay, so till this point we saw what is linear regression, what is gradient descent, drawbacks of machine learning, why deep learning shines, what exactly is a perceptron. Let's just quickly look at what is forward propagation. Okay, so the next topic is forward propagation. Okay, so I'll just quickly draw a simple neural network. This is my input, x1 x2. This is my neuron, and let's just say I have a simple network as of now. Okay, I'll just quickly run it like this. Okay, this is my active. This is my first layer's first activation. This is my first layer second activation, and this is my second layer's first activation. Okay, I'm not drawing out the weights as of now. I'll just quickly show you what exactly forward propagation means. Okay. All right. So we already know that what is forward propagation, but I will just quickly walk you through it. Right. So we saw that at each and individual neuron, what will happen is to calculate the output, right, or to calculate the activation. Let's say O11. This is nothing but the activation O11, and let's just say this is O21. Similarly, O211. To calculate the activation, what we are doing is we are doing a weighted sum of weights and inputs along adding it the bias. Then let's just say this weighted sum is, I am denoting it with Z. Then we are passing it into a activation function, and then we are calculating this activation. Okay. All right. So let's just say this is the activation of my first neuron. Similarly, for this particular neuron, I am calculating this activation. I'll just quickly walk you through. Like for example, summation of wi xi plus b is nothing but, for this particular neuron, is nothing but x1 into w first layers. This is my second neuron first input plus x2 into the weight of first layers second. All right. So what w122 means, this is your first layers second neurons second input. Okay, plus the bias. Okay, and later on what we are doing is we are denoting this whole summation as z, and we are passing it into an activation function. Okay, and it depends, if this is sigmoid, then it will output us the value in the range of 0 to 1. If it is some other activation function, then the range of that activation function will be different. Okay, and today's topic is not activation function. Just remember, activation function is something which takes the weighted sum and gives a desired output in the range of that particular function. Okay. All right, so I'll just quickly erase this, and I'll show you what forward propagation is. Yeah, right. Sorry. Yeah. See, at this point, you have calculated the weighted sum of the inputs with the weights, adding the bias, and you have calculated the activation of this particular neuron. Okay, let's just call it A11 for now, and let's just call the activation of the next neuron as A122. Okay, the same thing with small, denoting it with small a. Okay, we are giving this as an input for the next neuron. We are giving this as an input for the next neuron, and then we are multiplying this particular activation with the weight of this particular neuron. Similarly, we are multiplying this particular activation with this particular weight. Okay, so at this particular point, we are doing the weighted sum and adding the bias of this particular neuron. And similar to what we did earlier over here, we are passing it into a activation function, and then it will give us our output y hat, right? This is nothing but, this is called as forward propagation. Okay, forward propagation. Basically, you're propagating the data flow, the inputs as well as weights. You are propagating each neuron's output, passing it as input for the next neuron, and that is nothing but forward propagation, and you are eventually calculating your output. Okay, this simple process is nothing but forward propagation. Okay, and it basically helps you to calculate, to basically model your data. Okay, so model your data's distribution. Okay, so yeah, we initially saw what is linear regression, what is gradient descent, drawbacks of machine learning, everything perceptron. We saw forward propagation. Lastly, we'll just look at what exactly is back propagation. Okay, and I'll show you why back propagation is a very important concept in deep learning. as usual, we'll draw a very simple network. This is x1, this is x2, this is my first neuron, this is my second neuron, this is my last neuron, and this is nothing but my output. Okay. At this particular point, I'll just draw it I'll try to draw it as good as possible because I am not good at drawing. This is my first time doing something. This is my first time using stylus. Yeah, so it is a little difficult for me. Just bear with me for some time, right? So this is my first layer's first output. Similarly, this is my first second output. This is my second layer's first output. Okay, great. So in linear regression, or in the very first session, we saw that each the output, like for example, y hat is the output that depends on the summation of weights into your inputs plus bias term. Okay, but the thing is key, just a second, let's just denote it with the loss function, right? So loss is something which is nothing but your original labels minus your prediction model's predictions whole square, right? So later on we saw that your loss depends on two things, that is m and b, which is nothing but yi minus mxi minus b whole square, and this is just a model with one feature, right? But here you can see that you have two features, right? So we'll just quickly modify this equation into something like mxi, and I'll have to like modify this into, let's say this is nothing but m1 xi plus m2 x, let's just call this i1, and this is at i2 plus b. Okay, so this is my first input, this is my second input, this is my weight for my first input, and this is my weight for my second input. Okay, so at this particular point you can see that you have a four-dimensional distribution, right? For example, you have a loss. Your loss depends on three things: m1, m2, and bias, right? So if you try to draw this distribution, firstly you will not be, it is not possible to draw this particular distribution because it is a four-dimensional distribution, and we literally have a lot less features right now. But if we will try to draw this particular distribution, it will be a four-dimensional distribution, and of course we cannot imagine this. But eventually, as you have more features, you'll have higher dimensional distribution, right? For example, at this particular point, if you had, let's say, 1,000 features, right? 1,000 features, or let's call this inputs. If you would be having 1,000 features, then you will have roughly a very higher dimensional distribution. And as humans, we cannot imagine this, right? But we need to calculate something which is nothing but the gradient or the slope. I don't know why this is behaving weird at this point. Just a second. Right. So we need to calculate the gradients. Right. Let's just quickly look at this. Yi minus yi hat whole square. Right. So we need to calculate the value of weights and biases such that our loss is minimum. Right. And in neural networks, we have a lot of weights, right? For example, if you'll just quickly look over here, how many weights do we have? We have 1, 2, 3, 4, 5, 6, and 3 biases, right? So we have six weights, okay, and we have 3 bias, okay. So making it a total of 9 weights, and we have to tune these 9 weights in such a manner that our loss is minimal, right? So we did our prediction, okay. I'll just quickly walk you through what we did till now. We did forward propagation, and we saw that it is nothing but the flow from from your inputs to the output, right? And then you calculate your output. Then using this particular output, you calculate your loss, right? And then we try to tune our weights in such a manner that our loss is minimal. Okay, but the thing is, you can see that over here, this particular loss depends on this particular output. This particular output, or I can say this particular activation, depends on this weight, or I can also say that it depends on the output or the activation of my very first neuron in the first layer. And this particular neuron or this particular activation's value depends on, again, this particular weight, this input, right? So at this point we have to differentiate, or moreover I can say that we have to partially differentiate our loss with respect to all the weights and biases we have in our neural network, right? So for example, in the above example, we have 9 weights, right? So at this point, I don't know, this is behaving a little weird. Just give me a second. Right, so in the above example, we had 9 weights. Okay, so we'll have to partially differentiate our loss with respect to each of these 9 weights to calculate the gradient, to basically calculate this particular gradient, and use this in our optimization algorithm, that is nothing but gradient descent. Okay, so I'll just show you one example how to do this, and you can try it later on. You can try it on your own, right? So I'll just go to over here, okay, and I'll erase all this. I'll just quickly select this and I'll just delete it. Okay, yeah. Similarly, I'll select all this. I'll just delete it. All right, and I'll just make it a little better for you to understand. All right, so this is a lot of mess. We'll just draw our simple network again, right? So this is my input, this is my output. I have a neuron over here, I have a neuron over here. This is my last neuron, and from here I have my output, right? So just imagine on how many things my loss is dependent for now, right? So you'll see that I have my model's output over here. I can calculate the loss using MSE. Just imagine, just for now, just think we are solving a regression problem. So I'll just calculate my loss using mean squared error. And at this particular point, my loss depends on a lot of things. My loss depends on the activation of my third neuron, my second layer's first neuron. Then it also depends on these weights, right? So I'll just write it. This is the weight of second layer's first neuron, first weight. Similarly, second neurons, second layer's first neurons, second weight, right? Similarly, it also depends on all the activations before the preceding layer's activations, right? So it also depends on O1, and for first layers, second neuron, and all the weights, all these 4 weights over here, right? A lot of weights. I'm not writing it over here, but at this particular point, I'll just show you how you can differentiate how you can differentiate a loss function with respect to this particular weight, right? So this is nothing but W1, 1, 1, right? So this is my first layers. This is my layer 1. First layers, first neurons, first weight. Okay, so I'll just quickly show you how you can differentiate a loss function with respect to W11, W111. Okay. Yep. So let's start. I'll do partial differentiation, right? So if you are aware of what exactly partial differentiation is, well and good. If you are not, partial differentiation simply means that you are differentiating with respect to a single parameter, keeping all the other parameters constant. Okay, so I'll do dava L by dava W. Oh my god, I don't know why this is. I'm not able to write properly. All right, I'll just. All right, sorry, really sorry for this. I'll just do partial differentiation. This is called as dava with respect to my first layers, first in neurons, first weight. Okay, this is nothing but we know that we have to minimize the loss. So we'll differentiate the loss with respect to the last neuron's output, right? So my last neuron is nothing but my activation value of my last neuron. That is nothing but second layer's first neuron, right? I'll multiply this with nothing but the summation of my summation at this particular point, right? So these two activations multiplied by the weights of this particular edges, right? So this is, let's just write it like this, it will be more better. Let's just, for now, let's just write it like this, dava y hat, right? So y hat is my output. Okay, so I'll just multiply it with y hat with respect to this particular weights activation, and to, I have to go over here, this, right? So this particular neuron depends on the activation of my first layer's first neuron's activation, right? So what I'll do is I'll just quickly partially differentiate it with my first layer's first neuron, and then this particular activation depends on this particular weight, right? So I'll just quickly differentiate it with respect to my first layer's first neurons first weight. Okay, so this is a way how we are calculating gradients, or let's say slope, in deep learning. Okay, and this is just one example of how you basically calculate gradient. Okay, you will do this for all the remaining 8 weights of your network, right? So this is one of the weight. You will do this for all the remaining 8 weights, and then what we do is we simply update our weight. Right? So I'll just quickly draw it. This is x1, x2. This is my first neuron, second neuron, third neuron, and this is nothing but my output. Okay, I'm not drawing the edges right now, right? So what you do is you backpropagate. So what do I mean by backpropagate? You just go to each layer and we basically update each layer's weight, right? So for example, this was, let's say this was W111, right? So I'll say W1 new is nothing but W111 old minus my learning rate into my my learning rate. I don't know why this is coming out to be like this. W111 old minus learning rate times my partial differentiation, which we did above, right? So this is the partial differentiation, this one, right? This one, this particular thing, you will just replace it over here, and we will do this for all the remaining 8 weights. Okay, and once we calculate all the gradients with respect to each particular weight, we'll simply update it using backpropagation. Basically, you are moving from your output again to your input, right? And this is a continuous process until you have the minimum weight or the optimum value of your weights. Okay, so this was backpropagation. Okay, so I'll just quickly summarize the whole session. I hope I was able to at least give you intuition what happens in neural networks, right? So initially we saw linear regression, right? So we saw what linear regression does is linear regression basically tries to linearly model your data's distribution with respect to any number of feature available or with respect to any number of weights, right? So it tries to find the optimum value of the weights so that you can find the best fit line, which basically shows, which is very close to all the remaining data points of your distribution. Okay, after linear regression we saw gradient descent, right? So gradient descent is nothing but it is an optimization algorithm which is used in machine learning models to find the optimum value of your weights to reduce or to find the minimum value of your loss, right? Then we quickly looked at what are the differences between machine learning and deep learning, what were the drawbacks of machine learning, and why deep learning was able to overcome all those drawbacks. Next, we basically saw what exactly is a perceptron. And so perceptron is nothing but it is a basic unit of a neural network, and it is artificial neuron, which is a simple mimic of how our natural or biological neuron works. When you take a lot of neurons and you merge it into a layer, and when you connect all these layers together, you basically end up with something which is called as a neural network, right? So this over here, here is an example of a very deep neural network with three hidden layers, right? And one input and one output. Okay. Right. So we saw what exactly is perceptron. So perceptron basically does the weighted sum of your inputs with respect to the weights, and then it applies the activation function. Over here, the activation function is a step function. You can use other activation function also, but today we are not. Today's topic is not what is activation function. Today's topic is what are neural networks, right? So after perceptron, we saw multi-layer perceptron, which basically again is nothing but joining all the perceptron into layers, combining those layers, and making up a neural network, right? Next, we saw what exactly is forward propagation. So forward propagation is nothing but you are using the output of a single of individual neurons in your layer and sending them as input for the next layer, right? And you are doing until you get your result. Then you calculate the loss. You do then you try to partially differentiate your loss with respect to each parameter available in your neural network, and then you simply back propagate, and using gradient descent step you update your new weights, right? And this was it, guys. I hope I was making some sense and you were able to at least get some intuition on uh, what exactly deep learning is, and somewhat how neural network works, and what are the things which neural networks overcome, right? So just give me a thumbs up or anything so that I can just quickly move to the end of this session. All right, so I think we are good to end the session. If there are some doubts, I'll just quickly answer it and we'll end this session. All right, guys. So we will just end the session. Make sure you follow me on all the socials. I have the same username on all the socials. That is Hui Pranav. And yeah, don't forget to follow ML Nasik, who are bringing this particular all these good sessions to you guys. And yeah, that was it. Thank you. Uh, if possible, can you explain my query? Please do not ignore. Just a second, Ketan. I think there is some doubt. If possible, can you explain my query? Write a three-layered, fully connected network as a matrix multiplication. Please do not ignore. Okay. So you want a three-layered, fully connected network as a matrix multiplication. Um, yeah, it is possible. All right. So I'll just quickly. I'll just a second. Yep. I'll just quickly share my screen and I'll show you what this particular thing is. Okay, so if possible, write three-layered fully connected network is a matrix multiplication. Okay, so three-layered fully connected, right? So let's just say x1, x2, dot dot dot. Till we have xn. Then this is my first layer. Okay, so this is my first layer. let's just say at this point we have, let's just reduce this problem to some limited number of inputs. Okay, so let's just say I have three inputs. Okay, so I have something like uh, x1, x2, and x3. uh, you wanted me to show three layer, right? Three hidden layers, right? So this is my first neuron, this is my second neuron, this is my third neuron. Over here, let's say I have three neurons, and in the third layer I have two neurons, and in the last layer I have a single neuron. Okay, so I'm I'm not actually drawing all the edges, but because it will just get a lot complicated and it will just make it look very dirty, right? Not a very good drawing, right? So, but I'll just quickly show you. This is my first hidden layer. This is my second hidden layer. This is my third hidden layer. Okay. So you want a matrix form of all this, right? So I'll just write it over here, right? Okay. So for now, let's just imagine this is my first layer, right? So I have my first input, which is, let's just first do a simple summation, right? So we have summation of wi xi plus b. Okay, let's just first write all the weights. Okay, so I have w1 1 plus w1 my first neuron second weight plus w1 1 3. Okay, similarly I have first neurons second neurons first weight plus w1 2 2 plus w1 2 3. Okay, similarly we have w1 3 1 plus w1 3 2 plus w1 3 3. Right, over here we have this, these are all my weights. Similarly I have uh, my inputs, like let's say x1 x2 x3 plus I have my bias, right? So if I am right, so I have three biases, one b1 b2 b3, right? And this is my first hidden layer only, right? So this is my first hidden layer. I have three inputs, right? And we'll just, before multiplying, we'll take a transpose over here, right? Because as you can see, we'll be needing these three weights, these three, right? I'll just quickly show you, right? So if I can draw a single edge over here, this particular weight is nothing but w1 this particular weight is nothing but w1 and this is nothing but w1 Okay, so we are multiplying the three inputs with this particular three weights and adding the it to our bias, right? So taking the transpose and multiplying it. So I'll just write the very first row. You can write the rest of them, right? So w1 x1 plus w1 into x2 plus w1 into x3. Okay, and plus the bias, right? So b1. Okay, and yeah, the same thing you'll do for the rest two rows, and you'll have your output over here, and then we will pass it through the activation function. Okay, so this is nothing but over here we'll have our activation function. The same thing we'll do for these individual rows, and yeah, it's just the same, right? The same thing we'll do for the second hidden layer and the third hidden layer. Okay, I think yeah, I've cleared it out. All right, so yeah, I think I was able to clear it out. If there anything else, just let me know. Uh, I hope my screen is still visible. Yep. So thank you guys. That was it. Thank you so much for attending this particular session.